Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the laser diodes. Now let's start. So in this lecture I am going to cover about the introduction to the laser. Laser stands for light amplification by stimulated emission of radiation. Then the basic working principle, then the cavity based laser structure, optical feedback laser oscillation, then the laser modes, threshold condition for laser oscillation, and the numericals based on the problem. So what is a laser? So stimulated emission by the recombination of the injected carriers is encouraged in the semiconductor laser, also called by the provision of an optical cavity in the crystal structure in order to provide the feedback of photons. So this gives the laser several major advantages over other semiconductor, that is source, that is light emitting diode or the LED that may be used for optical communication. So these are as follows. So high radiance due to the amplifying effect of the stimulated emission, as the name suggests, and the injection laser which generally supply milliwatts of optical power. Then the narrow line width on the order of 1 nanometers or 10 angstroms or less, which is useful in minimizing the effect of the dispersion, that is a material dispersion. So the modulation capabilities which at present extend up to into the gigahertz range. So we are getting the capability up to gigahertz range and will undoubtedly be improved upon. So relative temporal coherence, which is considered essential to allow the heterodyne means when we are talking about two different wavelengths. So in coherent system we are having the homodyne and the heterodyne, but we are talking about the heterodyne where we are considering the local oscillator and the input wavelength both are different. Detection in a high capacity system, but at present is primarily used in the single mode systems. So good spatial coherence which allows the output to be focused by the lens into a spot which has a greater intensity than the dispersed unfocused emission. So this permits efficient coupling of the optical output power into the fiber, even for the fibers with low numerical aperture. So what is the basic principle of laser? So laser is a device which amplifies light, and it stands for light amplification by stimulated emission of radiation. So the operation of the device may be described by the formation of an electromagnetic standing wave within a cavity which provides an output of monochromatic, only a single wavelength, highly coherent radiation. So the emission process can occur in two ways. So we are having two different methods of the emission, either the spontaneous emission, this we have seen in LED structure and LEDs, which an atom returns to the lower energy state in an entirely random manner. So in a stimulated emission, when a photon having an energy equal to the energy difference between the two states, that is E2 minus E1, interacts with an atom in the upper energy state, causing it to return to the lower energy state with the creation of the second photon. So this is the stimulated emission process. So however, it gives the laser its spatial property as an optical source. So firstly, the photon produced by the stimulated emission is generally of an identical energy to the one which caused it, and hence the light associated with them is of the same frequency. Secondly, the light associated with the stimulating and the stimulated photon is in phase and has the same polarization. Therefore, coherent radiation is obtained. The population inversion. So, another important keyword in the radiation process is the population inversion. To achieve the optical amplification, it is necessary to create a non-equilibrium distribution of atoms such that the atom of the upper energy level is greater than that of the lower energy level. So, this condition, which is known as the population inversion. So, this process is achieved using an external energy source and is referred to as pumping. As we can see in this diagram, we are having the atom in the lower energy state. It is having the transition from the lower energy to the higher energy due to the absorption of radiation, and we are getting the atom in the higher energy state. So, this is the energy, external energy which we have provided. So, this process is known as the absorption. The second process is the spontaneous emission. In spontaneous emission, when we have the atom in the final state, or you can say higher energy state, it's returned back, it's have the tendency to return back to its lower energy state. So, when it returns back, it releases its energy. Now, this energy is in form of photons, and the energy is the photon wavelength is equals to the difference in the energy bands or the gaps. The another mechanism is the stimulated emission. Now, we have the atom in the higher energy state. Now, the external energy is provided, and this external energy is equal to the band gap. Now, due to this, it's have the transition from the higher energy state to the lower energy state, and due to this transition, we have the two photon, one which is generated by the transition, another one which is fed through. Now, we are having the two photons at the same time. So, this process is known as the stimulated emission. So, the energy state diagram showing the absorption is spontaneous emission and the stimulated emission. The black dot indicates the state of the atom before and the after transition take place. Now, the next thing is the cavity based laser structures. So, and the optical feedback, laser oscillation, resonant cavity, and laser modes. So, light amplification in the laser occurs when a photon colliding with an atom in the excited energy state causes the stimulated emission of a second photon, and then both these photons release two or more photons. So, continuation of this process effectively creates the avalanche multiplication. To achieve this laser action, it is necessary to contain photons within the laser medium and maintain the conditions for coherence. So, we are getting a coherent light. So, this is accomplished by placing or forming mirrors, or that is a plane or the curved mirrors at end or either end of the amplifying medium as shown in the figure. Let's see. So, we are having two mirrors having apart by the distance, that is capital L, and this is the partial reflecting mirror. We are getting the output, that is the optical output from this mirror. So, we have an amplifying medium between the two mirrors. So, it provides the positive feedback of the photons by reflection at the mirror. So, here we have the reflecting mirror, and here we have the partial reflecting mirror. So, reflection at the mirrors at the either end of the cavity, and hence the optical signal is fed many times while receiving amplification as it passes through the medium, and the structure therefore act as a Fabry-Perot resonator. So, this structure is known as the Fabry-Perot resonator. So although the amplification of the signal from the single pass through the medium is quite small, after multiple passes the net gain can be large. So one mirror is made partially transmitting, useful radiation may escape from the cavity, that is this one, the mirror 2. If this is mirror 1, which is a reflecting mirror, this is the partial reflecting or transmitting mirror. So the structure forms a resonant cavity when sufficient population inversion exists in the amplifying medium. The radiation builds up and becomes established as a standing waves between the mirrors. So these standing waves exist at the frequencies for which the distance between the mirror is an integral number of the half wavelengths. Thus, for the optical spacing between the mirror is capital L, the resonance condition along the axis of the cavity is given by, that is, lambda q by 2n. So discrete emission frequency f is defined by, that is, q c by 2 times of n into the spacing capital L. So the different frequencies of the oscillation within the laser cavity are determined by various integer values of q and either constitutes a resonance or the mode. So it is creating the resonance or the mode. So when L is along the longitude axis of the structure, as we have seen in this figure, we have the capital L. So when L is along the longitudinal axis of the structure, the frequency given are known as the longitudinal or the axial modes. So these modes are separated by the frequency interval. So frequency interval can be determined by C by twice of n times into L. So mode in terms, that is a free space wavelength, is given by, that is, del lambda, that is equals to lambda square by 2 n L, where del n is nothing but lambda del f by f and lambda square by c into del f. So large number of modes may be generated within the laser cavity, that is, the spectral output from the device is defined by the gain curve. So here we can see the intensity versus the frequency. As we can see that at a regular interval we are having the constant intensities, and it is separated by C by 2 n times of L. If we compare the intensity versus the frequency curve, in the case of the longitudinal modes in the laser, we are at a particular frequency, we are having the maximum intensity. So the lower order transverse modes of the laser we can see. Here we have the different transverse modes of the laser, that is a laser optical cavity mirror. And here we have the TEM00 mode, where we have the electric field vectors all aligned upwards. When we talk about the TEM10 mode, we are having the upward and the downward electric field or the magnetic field, and TEM11, as we can see, it's having the flower like structure where we have the electric field upward as well as downwards. So there is one numerical based on this problem. So a ruby laser contains a crystal of length 4 centimeters with a refractive index of 1.78. The peak emission wavelength from the device is 0.55 micrometers. Determine the number of longitudinal modes and their frequency separation. So the number of the longitudinal modes supported within the structure may be obtained, that is Q, that is given by 2 times n into L by lambda, as we have seen earlier. Here we can see the formula of Q, that is F equals to QC by 2 n L. The same formula is used here to solve, and we can solve the Q. So the frequency separation of the mode, that is given by del F, we can calculate, that is 2.998 into 10 to the power 8 divided by 2 times into 1.78 into 0.0 0.04, where we have the refractive index N, that is 1.78, and the length of the crystal, that is capital L, is 4 centimeters and small n is 1.78. We are getting 2.1 gigahertz. Now what will be the condition for the threshold in case of the laser's oscillation? So the steady state condition for the laser oscillation are achieved when the gain in the amplifying medium exactly balances the total loss. So a minimum or the threshold gain within the amplifying medium must be attained such that the laser oscillations are initiated and sustained. So this threshold gain may be determined by considering the change in the energy of a light beam as it passes through the amplifying medium. So the amplifying medium occupies a length L, completely filling the region between the two mirrors, which have the reflectivities given by R1 and R2. On each round trip, the beam passes through the medium twice, hence the fractional loss incurred by the light beam is given by, that is a fractional loss having the formula reflectivities R1, R2 exponential of minus 2 alpha times of the spacing between the mirrors, that is capital L. So the gain coefficient per unit length produced by the stimulated emission is given by G, that is per centimeter. So fractional round trip gain is given by, we have the exponential gain multiplied by L. So we have the stimulated emission which is given by G per centimeter. So hence we can write that is the exponential of G times of L multiply with the reflectivities of the mirrors, that is R1 and R2 respectively, exponential of minus 2 alpha into L, so that will be equals to 1. So we can write further it as, that is R1 R2 exponential, that is G bar minus alpha bar into the length, that is the spacing between the mirror, that is equals to 1. So the threshold gain per unit length may be obtained by rearranging the above expression to give, that is a Gth term we can calculate, that is alpha bar plus 1 by 2 L log and 1 by R1 into R2. So there is one numerical based on the formula which we have derived here. Here we have derived, that is a Gth term, that is the gain coefficient. So gain coefficient for the stimulated emission, we are having alpha bar plus 1 by 2L log with the base E. So ln we are having the log with the base E, 1 by R1 into R2. So let's solve this problem. So an injection laser has an active cavity with losses of 30 per centimeter. So already gain is given, and the reflectivities of the each cleaved. So we are having 30 centimeters is not G, this is per centimeter, that is means alpha bar is given to us, and the reflectivity of each cleaved laser facet is given by 30%. So determine the laser gain coefficient for the cavity when it is having the length given by 600 micrometer. So the threshold gain per unit length, where when we consider the reflectivities, that is R1 equals to R2 equals to R, that is given by, so again the equation is reduced to, that is Gth term, that is alpha, and we are having 1 by 2L. So if you substitute here, that is R1 equals to R2, what we had is, we have the Gth term, that is alpha plus 1 by 2L and log, that is ln with the base E, 1 by R1 into R1, or you can say R into R, both are the same. So we have R square, so 1 by R square we can write it as, that is Gth term alpha plus 1 by 2L ln and 1 by R square. So 1 by R square we can take in front, so we are having that is Gth term, that is alpha, plus this power term we can take outside, that is 2 and 2L ln 1 by R. So this 2 and 2 will be cancelled out. What we get is this term, that is alpha plus 1 by L log with a 1 by R. We have the reflectivity. Now substituting the values, so we have the value of alpha, that is given by 30 per centimeters. Then we have the length is given by 600 micrometers, that is capital L. So we are having 30 plus 1 by 0.06 plus reflectivity, that is 30%. So 30% means 0.3. So we are getting the gain coefficient, that is Gth term, that is given by 50 per centimeter. So the threshold gain per unit length is equivalent to the laser gain coefficient for the active cavity, which is 50 per centimeter, and this term sometimes expressed in terms of 1 by L or 1 by R. So therefore, where R is the reflectivity of the mirrored end is equals to under root of R1 R2. So in this lecture, we have introduced about the laser and the phenomena, how the laser works, the basic working principle based on the stimulated emission and the energy band diagram. Then we have discussed about the cavity based laser structure, where we have used the mirrors separated by the distance capital L. Then we have discussed about the optical feedback, that is laser oscillation and the resonances and the laser modes. So different modes we have discussed, that is TEM00, TEM11 and the laser lines and the threshold condition, and based on the threshold condition we have calculated the gain coefficient, that is Gth, and the numericals based on the problems and the formula which we have derived. The reference for this material is the optical fiber communication, that is principle and practices by John and Senior. Thank you.